Beginning at the Continental Divide, the Firehole River of Yellowstone National Park flows and tumbles along, picking up waters from the Geyser Basin, including Old Faithful, and downstream just a few miles, the waters of Grand Prismatic Spring join in. Soon it joins the Gibbon River to form the majestic Madison River, which works its way out of Yellowstone, forming spectacular valleys and providing amazing fishing. Then it joins the Jefferson and Gallatin rivers to form the mighty and historic Missouri River. It also carves amazing valleys and canyons as it bursts out into the upper Great Plains. Continuing its journey northward, it crosses into Canada and finally empties into the Arctic waters of Hudson Bay. Hudson Bay? The Missouri doesn't empty into Hudson Bay. It turns southward to join the mighty Mississippi and ultimately empty into the Gulf of Mexico. But not long ago, it did flow into the Hudson Bay. We will learn how geologists figured this amazing history out and why the river dramatically changed its course.
Hello, I'm Myron Cook. I'm standing on the bank of the historic Missouri River, just 50 miles or so south of the Canadian border, near Big Sandy, Montana, at a historic landing that's named Coal Banks. And it was quite an active place during the gold rush, the Montana gold rush of the late 1800s. And of course, Lewis and Clark passed through here in 1805 on their historic expedition. Isn't it amazing to think that this river, which currently swings to the south, meets the Mississippi near St. Louis, Missouri, and continues on clear down into the Gulf of Mexico, at one time flowed northeast. Not to the south, flowed northeast into Canada and clear into the Hudson Bay. How did geologists know that? Well, it's for that very reason that I made this long drive to right at this point. Because right here is where the Missouri River makes an abrupt change in direction and starts going south. Now, when geologists look at any river and they see an unusual change in direction, they're suspicious. They're thinking, why did it do that? And they go and study the area. So geologists studied this area here, and that's when they learned that the Missouri at one time flowed to the northeast into Canada, and then switched right here to go to the south later. And there are other keys that they used, other methods, and we're going to learn about those, so let's get going.
Let's go from Coal Banks to the south some 175 miles to the iconic Yellowstone River north of Yellowstone National Park, where we can learn some geologic principles used to unravel the histories of rivers.
I'm standing on the banks of the iconic Yellowstone River in the aptly named Paradise Valley. It started its journey in the highlands mountains of Wyoming, working its way down, forming the magnificent Yellowstone Lake, continuing on, tumbling over the upper and lower falls of the Grand Canyon of the Yellowstone, continuing on out, working its way to right here just a few miles before it breaks out into the Great Plains. And it's here that I want to show you a few features that inform geologists of a river's history.
Notice this flat-topped hill. It's a river terrace. They typically have a cap of cobbles and gravel. Zooming in, we see the gravels top this terrace. Note all the gravel in this small landslide and also the gravel scattered along the top here. I like this view because in the foreground we see a nice gravel bar deposited by the river, which is a similar process that occurred to deposit the gravels on the terraces we have examined. Looking carefully, we see evidence for another terrace about 20 feet below the main one right in this area. As you can see, the upper terrace covers a large area, and in fact at one time it covered a much larger area. We'll learn about that using the whiteboard.
To the whiteboard we go. Now, I've put my famous little tree here so we make sure we understand we're looking sideways, cross-sectional view. This is just the land surface, and I've put a river that's cut a nice notch into the land here. Now, today, most of the rivers are erosional in nature. There are some that are not, but most of them are erosional, and they're cutting down. So let me do that. They're cutting down and sideways. So they might move over here through time and put a new channel here, like that. And then maybe it jumps over here and puts one here, and it keeps continuing. Now in map view, I've done a little sketch here. The two black lines here on the side are the broader river valley, and I've got the river going through here. And of course, through time, it moves around, and it just keeps cutting this broad valley as this river cuts sideways and jumps around, avulses we call it, and just continually cutting over that valley. And the process just continues. Let me erase here. It goes here in cross-sectional view, etc. And it also can go down another level, deeper. So it can go to another deeper level and keep going and building like so and cutting all this material out. Okay, so the river has cut this big broad valley back and forth and down. Now it turns out that in interglacial periods like we're in now, rivers tend to be erosional.
The Madison River, a major tributary to the Missouri, is a good example of a river that is currently downcutting.
But the climate can change and the glaciers come back, and this has occurred many times, as you probably know. So let's change that climate. Let's introduce glaciers. And when glaciers come along, boy, they provide a lot of material because they're so powerful. They just erode the rock and they tear it up and they bring it into the river systems and they overwhelm those systems. And it builds a grading system where it builds up. And the river types change. They change to an anastomosing or a braided river system. Let me sketch that. So here it starts putting in gravels, these river systems, a whole blanket of them, all across, all fills in these anastomosing systems and grades and builds up.
The Beely River of New Zealand is a nice example of a braided river that is filling the width of the river valley.
But of course, the climate can change again, and we can go into an interglacial, and erosion can begin anew. So here I'll put a channel right here. The river starts cutting back down like this. And it starts migrating and cutting deeper all through here and cutting everything out, or much of it. So I'll do that here. It starts here, cuts deep, deep, and we'll say it goes to right here and cuts a whole new river valley. Wow. So with this renewed erosion, we've cut another river valley. But look what we have left over here. We have remnants of that graded system, that big sheet of gravels and cobbles, right here and here. And those are the river terraces. That's what we've been seeing. And see how much information that gives you when you can find a flat-topped terrace like this along a river. You start to develop a history picture in your mind. But let's continue with this because it's cyclical and the climate changes again and it grades yet again. So we've graded with these braided systems and built up another big thick gravel sheet. They can be quite thick. I've personally seen them 50 feet thick or so. I'm sure they get a lot thicker than that. But because of all the glacial material and the change in climate. But let's put the one last cycle in where we've graded, the glaciers have receded, and now it starts to downcut. And I'll put that last phase in. So with this final phase I've put in, which actually represents pretty well today because we are in an interglacial period, we've eroded again and we've left behind terraces again. Now it's important to note that these terraces don't necessarily exist all along the river. There can be small remnants, very small remnants. Sometimes they're easy to see and big, like some we've seen, but other times they might only cover or be in an area of a few acres. So, but even a small piece, even a hint of a terrace that you feel pretty good about as a geologist tells you a lot of history about that river. So here I've got a small terrace here and a better developed one here in this particular sketch with this eroded river canyon, or river valley, I should say, through here.
If you look carefully, you can see 3 terraces here along the lower Madison River Valley. Returning to the terrace at the Yellowstone River, notice the anastomosing river patterns. It sure reminds you of the New Zealand example.
With an understanding of how rivers work, you can begin to see Earth's history through time. Now, that gets exciting. I hope you get a chance to do that as you're out hiking in nature, or maybe you're just driving through the countryside in your car. Much of the work that I do is visualization in my own mind about what the Earth must have been like as I make the observations as I'm out and about. Well, since geology is so much about what you visualize in your head when you think about these ancient systems, let's do an imaginary field trip together. Let's go hiking across the northern Great Plains with the gentle rolling hills. So we're hiking along and we come to a valley. We look in this beautiful valley, but there's no river. And we wonder about, well, how did this valley form? So we decide together to look for clues. First of all, we note that it's quite long and it has some gentle bends in it, which is kind of like a river, but gosh, I don't know. But then we make a critical observation. We see a remnant river terrace. Now we feel confident, and boy is this exciting, because we can say that this was a river that created this valley, and it was a big river because it's a nice big wide valley. But now even more fun. Well, what happened to the river? So to answer that question, we broaden our investigation and we head to the north and we come to the Milk River and we start looking at that. And we make some curious observations, some critical ones, I should say, that really make us think. And with all these observations, we start to realize what really happened.
Let's take a look at the Milk River and learn why geologists found it so interesting. Flying eastward downriver, we see that the river is modest in size and that the valley it cuts is about 1/4 to a half-mile wide. In this area, the river valley seems to widen. By the time you get to the community of Chinook and eastward, it becomes quite obvious. The river valley now is typically 2 to 3 miles wide rather than the upriver valley, which is less than a half-mile wide. And the river isn't significantly different in size. Now, what could cause that?
This is what science is all about, and it gets me excited every time it happens. Making a series of observations that seem to be related somehow, and developing a hypothesis to explain how. I hope you're having fun thinking of possibilities. I think we need to go to the whiteboard. So I have a sketch here in map view of some of the main features we've been talking about. First of all, we have the Missouri River, the modern configuration here. In blue, it's moving along to the northeast, and then near Coal Banks, it turns to the southeast. The 2 red lines here represent this broad valley that we've been looking at. And these mountains here are the Bear's Paw Mountains, and this is the Milk River. And this little black piece here I've sketched is just a remnant river terrace that makes us feel confident about that this valley formed by a river. And I think it's important to re-emphasize that this valley, when you look at it today, is sloping to the north, away from the river, which is exactly the opposite of what you'd think. Valleys slope into rivers, not away from them. So that's an interesting observation. Okay, so I know a lot of you are ahead of me on this, but this is the valley of the ancient Missouri River. Actually, it's not that ancient for geologists. It didn't happen that long ago. We'll be talking about that here in a bit. But so the Missouri River flowed here, and it is what carved this broad, big valley. And that explains what's happening at the Milk River. The Milk River in this section has a normal sized valley for that size of river. But it enters and goes down the ancient Missouri River Valley. It didn't carve this valley. The Missouri River did, and it continued on.
Now it's time to expand on these observations. The broad valley we observed extends from the Coal Banks area to the north along the western flank of the Bears Paw Mountains. Looking at this shaded relief map, we can see it quite clearly. The center of the valley runs along this line. The darker green area here indicates a lower elevation and signifies that this valley slopes to the north away from the Missouri River. Following the valley to the north, we see that it intersects the Milk River, and wouldn't you know it, the intersection is right where the Milk River changed from being within a modest width valley to the much wider valley we observed. So the ancient Missouri River started at the Big Bend and wrapped its way around the Bears Paw Mountains to intersect the modern-day Milk River and continue down that valley for some distance. Then it veered to the north again to make its final journey to the Hudson Bay. Isn't science fun? Now it's time to determine why the Missouri River changed course.
We've been focusing on what happened to the Missouri River, and of course we want to know why it happened. And it's for that very reason that I'm here some 30 miles north of Williston, North Dakota. This is new country for me, wide open spaces. But at any rate, I came to this very lake here, small lake, because it turns out it holds a critical key into understanding why it happened. So with that, we're going to get a broader perspective using the drone and Google Earth.
This lake just seems to be a hole in the ground right out in the middle of the relatively flat country. Looking from far above, this is the lake of interest. Boy, there's sure a lot of lakes around here. I've never seen so many. In reality, there are even more than I could have imagined. Thousands and thousands of lakes. Notice that they occur in a band, and it continues much further to the south.
The thousands of lakes that we've been looking at are referred to as Kettle lakes, and they're associated with continental glaciation. And I've drawn a big continental glacier here. But first I want to tell you something kind of funny. I had been looking on Google Earth for a nice Kettle lake that was close, relatively close. Let me tell you, it was a long drive, but close to me to drive to. And that was north of Williston, North Dakota. I found this nice lake on Google Earth. And I drive up there through Williston, I get there, and a sign near that small lake there, you know what the name of it was? Kettle Lake. I thought that was kind of funny. Okay, the big glacier here. And let me tell you, these continental glaciers are huge, and I'm sure most of you know that. But back in the core of this giant ice sheet, the Laurentide ice sheet they would call it, it was up to 2 miles thick over Hudson Bay. And out in the front, of course, as it's getting to the front where it's the balance between melting and glaciers, it could easily be 1,000 feet thick. I mean, this is hard to really imagine. And I think it's really important to think about scale. So if we say that the front of this is just 1,000 feet thick, which I think is fairly reasonable, how tall would a 10-story building be if I sketched it right here? Let me show you. It would be about this tall. right here. That's a 10-story building. So that helps us think about the scale. Fortunately for us, the climate changed and it became warmer, as I've depicted here by the sun, and started to melt these glaciers, and they started to recede back. And there are a couple interesting things happening. First of all, they leave big chunks of ice out front. They can leave them out here. And of course, they can be all different sizes, but I'll put a couple big blocks of ice out here. And also, as they recede, all this material that the glacier has been depositing, remember I've depicted that with all these black little dots and stuff, or gravels and cobbles and boulders and sand, everything that have been plucked off the ground. I mean, it just literally plucks it off the ground and wears down the ground, like tremendously erosive power. And depositing out here in front. Now, with all this extra water, it starts redepositing that material as an outwash plain. That's what they call it. And it's flushing it out and depositing it, and it fills in around these big blocks of ice. So I'll draw that as it deposits that outwash material all around these blocks of ice. A big fan of material that's deposited out. And of course, at some time, these ice blocks melt, and it leaves big holes in the ground, which become the Kettle Lakes. And they can be big. They can be up to 8 miles across or so, 150 feet deep, these holes that become the lakes. So really an amazing process.
There are other clear signs of glaciation in the region. Are you familiar with these ridge-like features?
A quick discussion on end moraines. I have my continental glacier here, and as it's coming forward and depositing all this material, it can act kind of like a big bulldozer and push up lots of material in front of it, like so. And also there's just plain deposition building up in front of it as the melting, you know, right at the front leading edge. But there's this bulldozing effect. Now, if you think about it, the glacier can recede. It goes back and forth. As it recedes, it doesn't just steadily recede back. It can cycle back and forth. Let me show you something. So if we recede it back a bit, and I'll put the front of it right here, it can start building a new moraine and pushing a new ridge out in front. So I do that, and I put another ridge here like this. And you can just stack these in, one ridge after another of material all along the front of this glacier. And the end one, the very end one's called a terminal moraine, and all the others are end moraines.
This is a nice example of an end moraine in Greenland. Note the outwash plain out in front of it. And here is a neat glacier with its end moraine in Nunavut, Canada. So now when we see these moraines, we can visualize a large lobe of the glacier pushing forward. Even better, you can search for and find more of these using Google Earth. So there you have it. The massive Laurentide ice sheet forced not only the Missouri to turn south, but also the Yellowstone and Little Missouri rivers. Indeed, nearly all the waters of Yellowstone National Park flowed into the Hudson Bay before being forcefully diverted to the south about 70,000 years ago. As you can see from this map, the modern Missouri closely follows the edge of the glacier that was active from about 70,000 years to 10,000 years ago and is named the Wisconsin Glacial Stage. This is like yesterday for geologists.
Well, I've enjoyed this journey, and I hope you have too. Would you consider subscribing? You can do that by clicking on that button that has my face on it. Thank you for watching.